All right, good morning, everyone. And today we'll go over, well, today is one of the most important classes or lecture talks for the entire quarter because without these concepts, the rest of the quarter is going to be a blur. Okay. So mostly it's all about concepts and explanation of the math and how you're going to use it. Before I begin, I have a few things going on today. So I have a workshop and a seminar I'm attending, training not training, seminar and a workshop that ends at 2, right? From right at 12 until 2. Then we also have the E department industrial advisory board meetings all day. And so I won't be available for office hours at my usual time. If you have a question, send me an email. I'd be able to answer emails. Also, I'd be happy to meet over Zoom later today or over the weekend, and then possibly in person from 4 to 5 p.m. today. So I have like meetings and workshops, seminars, just back to back to back. So just a packed schedule for today. I'll also post an announcement on Canvas, but I just wanted to let everybody know right now, at least those who are attending right now in person and online, that if you come by for office hours, come after 4 o'clock, okay, not before then. Okay, so as I was saying, very important topic for today. So let's go to our class notebook. And section 4, we introduced phasors, and I stopped right there. Okay, so we talked about how we are going to use complex numbers to make the math less complex. Okay, if you think back to chapter 3, voltage and current for inductors and capacitors. For a inductor, voltage is L di over dt, derivative of the current. If you want to find the voltage, you integrate the current. Now you introduced a time varying signal in that equation, sine x and cos x, with the phase angle. It's complicated. You have differential equations. So in order to avoid solving that complex math, we use complex numbers. And what that allows us to do is we can apply all of our equations that we learned in chapters 1 and 2 exactly the way they are written. Okay, so Ohm's law, KVL, KCL, mesh current analysis, node voltage, everything works exactly the same way, except now we introduce complex numbers in there, right? And the math that we're going to look at is not exclusive to electrical engineering, right? The math is generic in the sense that it applies to all scientific fields. Even in your own areas, in your own fields, you may have come across this, or at some point you will. Okay, so this math that we're going to look at is again applies to all scientific fields. Okay, so phasor we looked at is a time domain, it's a frequency domain representation of a time varying expression. So we have V of t given by Vm cos of omega t plus theta. We can represent it as a rotating vector in the complex plane. Okay, the rotating vector is rotating counterclockwise with a speed of omega. Omega is 2 pi f. Where f is the frequency in hertz. Even though we say it is a rotating vector, that vector is not actually rotating. That phasor is simply a single snapshot of one instant in time. Okay, and that instant is here. Oh wait. Okay, so that instance in time, we take a snapshot of that time varying voltage or current, and we represent it as a vector. And that vector is known as a phasor. The transform is known as a phasor transform. There is a derivation, of course. We don't usually cover the derivation in non-E major classes. Vector needs only two things to describe it: magnitude and direction. We obtain those directly from the expression for V of t or I of t, as the case may be. The peak value or the magnitude gives us the length of the vector, and the phase shift gives us the angle. Hence, it is also known as the phase angle. And this is the reason why we keep the phase in degrees and not in radians, because we want to describe it as a vector. Okay. So phasor for V is Vm with an angle of theta. Phasor for current I would be Im or I peak with an angle of theta. So voltages and currents are represented using complex numbers. Right. Now, if you look at that vector, forms a right angle triangle. The projection of the vector on the real and imaginary axis forms a right angle triangle. As I was saying, there is a derivation, right? So in order to directly write this transform, the expression must be in cosine. Expression must be in cosine. If it's not, you use this trigonometric identity and you convert it into cosine. Sin x is cos of x minus 90. It's a right angle triangle. You have a 90-degree angle at the far end. The other two angles combine to give you 90 degrees. So sine of x becomes cos of x minus 90. So if you have a current or voltage, sine of 200 pi t, if you want to write it as a phasor, you have to subtract 90 degrees from that expression. If there is a phase angle in there, like say plus 30, then you subtract 90 degrees from there. If a phase angle is not there, it means it's 0, then it's simply minus 90. And we will see that in the examples going forward. But this is an important note to keep in mind. The expression must be in cosine. Okay. All right. Then this is, again, one of the most important concepts, impedance. So don't worry about writing anything down. You already have access to all the equations, but look at the words here, okay? Resistance comes from the word resist. It resists the flow of current, okay? It resists the flow of current. From here, we're going to introduce two new terms, reactance and impedance. Comes from the word react, impedance from impede. All three of them are synonyms of each other. Okay, so let's talk about reactance first. Excuse me. Reactance is associated with energy storage devices. The only energy storage devices we have are inductors and capacitors. Resistors do not have energy storage capability. So resistors behave exactly the same way for AC as they do for DC. No change, no difference. So resistance is resistance. However, inductors and capacitors, especially ideal ones, do not have any resistance because they do not resist the flow of current. Right? They do not resist the flow of current. So they don't have resistance. They are zero. Okay? The resistance for an inductor and capacitor is zero. However, the energy that is stored in these components, in the magnetic field and the electric field, will oppose or will impede, oppose or impede any change in the input. Again, critical difference between the two, or important difference, important distinction between the two. They do not resist the input, but they oppose any change in the input. Okay, and that has a physical manifestation. It is a physical phenomena. It is termed as reactance, because It is reacting to any change in the input voltage or the input current. Okay. So again, an inductor or capacitor do not resist any change in the input voltage or the input current, but the stored energy will oppose any change in the input. And that opposition, we call it as reactance. So take 10 seconds, think on that. Let me know if you have any questions. Good so far? Okay, so then reactance is not something you would hear or read about in everyday life. What you will hear or read is impedance. And impedance is a complex number, it's a complex quantity that combines both resistance and reactance. And because we are using complex numbers to represent it, we say, or not we say, we represent resistance with the real component, and we represent reactance with the imaginary number or the imaginary component J. So Z, impedance is represented with Z. Z is a summation of the total reactance and the total resistance present in that component or that circuit. And mathematically, we write the expression R plus JX. J, of course, is the imaginary number I. R plus JX. So it's kind of the opposite of phasor. In the phasor, we first have the vector, we have the magnitude and the phase angle, and then we can not transform, but we can change those polar coordinates into rectangular coordinates. Here, we already have the rectangular coordinates. We can transform those into polar coordinates and portray impedance as a vector. It is not a rotating vector, it's simply a vector, that's all. It's a vector in the complex plane. Now, the important thing to keep in mind is resistance is real, reactance is real, impedance is the sum of the two. So impedance is also real. But what you will always read or always hear is imaginary reactance. That reactance is not imaginary. That reactance has a physical basis. It is very real. It is not a figment of somebody's imagination. When it says imaginary reactance, it is only talking about the mathematical representation of that reactance. Again, as I said, reactance is opposition from the stored energy. So it has a physical basis. It is real. Okay. But you will often hear or read imaginary reactance. It's stating mathematical representation of the reactance. So it's an important point, important distinction that I want students to be aware of. All right, any questions? Yes. Yeah, we just represented using the imaginary number. Yeah, that's why we call it imaginary reactance. As a student, when I first started out, I had a hard time grasping. This was like, again, 30, 35 years ago. And it took me a long time to understand. It's actually, it's not imaginary. It's not, it's like, if it's imaginary, then why are we studying it? Why does it make a difference? It's a mathematical representation that is imaginary, but the phenomena is very real. So I always make it a point to, illustrate, harp on it. So impedance Z is R plus JX. You transform it into the vector, you get magnitude of Z, and you get a phase angle for Z. If you connect all three, you get what is known as the impedance triangle. Impedance triangle. Real axis, imaginary axis, you have the vector. Length of the vector is magnitude of the impedance, and the phase angle it makes is theta. And the projection of that vector, of course, is the pure resistance R and imaginary reactance X. So yeah, you would read that terms the pure resistance and imaginary reactance. I've heard that too. So different books, different authors, different people will use different terms, but these are the most generic terms that are associated with resistance and reactance. As you see here on the screen, reactance is represented with uppercase X. Resistance is, as always, uppercase R. Impedance is Z. More often than not, I always like to say they are synonyms of each other. Resist, react, impede. Okay. And the symbols for all three are also the same. No different. Units are also the same. Okay, ohms. As a real life example, I would point out speakers, any kind of speaker. Right now I have this wireless headset. This wireless headset has two speakers. We have speakers in the classroom, plus plus I have this microphone. The microphone is the opposite of a speaker. It captures the sound waves, captures my voice, and converts the sound waves into electrical waves or electrical signals. Speakers are the exact opposite. Speakers will convert electrical signals into sound waves. So very quick, brief operation or explanation. Speaker has a coil around a magnet. That coil is an inductor in a magnet, right, in a magnetic field. When electrical signals pass through it, magnetic field is set up. When the frequency changes, depending on who's talking or his squeaky voice, the frequency changes. Volume or the amplitude changes. So the frequency changes, the amplitude or the magnitude changes. The inductance magnetic field will oppose that change. Okay. But because it is being forced to change, that electrical signal is now going to physically move that paper cone. And that's how an electrical signal is converted into sound waves. Okay. It's an inductive coil, so it has impedance. So if you pull the spec sheet of any home theater system or any sound bar or any speaker from the website, from the internet, that specification will always state the impedance in ohms. It'll always state 4 ohms impedance, 6 ohms impedance, 8 ohm impedance. Headphones are usually 32 ohms impedance. Okay, you'll never see the words reactance. You'll never see the words reactance. You'll always see impedance, because impedance will comprise both resistance as well as reactance, both together. Okay, and of course, it's not a fixed quantity. The impedance will change depending on the frequency of the incoming signal. As we see in the mathematical expression here, depends on the frequency. And impedance of the inductor and impedance of the capacitor depends on the frequency. And I will explain how and why. Yes. Quality of the speaker, it just depends on current handling capability. So lower impedances would require a high current. You'd have to match. So it goes back to the Thevenin resistance. You have to match the speaker to the output of your amplifier. If the output of the amplifier is rated for 4 ohms, you have to match a 4 ohm speaker to that one. And if the output of the amplifier is 8 ohms, you have to match that one. So it happened to me. I was playing a gig a long time ago, and had an amplifier that was 8 ohm speaker, and I connected a 4 ohm speaker to it. I didn't know it was 4 ohms. I matched it up, and an hour later, everybody could smell something burning. And so the coil of the speaker got heated up because it's a lower impedance. It's now sending a whole lot more current through it, or it's pulling a whole lot more current through the output of the amplifier. And so it got heated up. And so everybody could smell a burning. It wasn't like smoke coming out, but you could smell it. And it took me a while to figure out what was going on. So you have to match the speakers to your amplifier. Thevenin resistance of the speaker should match the Thevenin resistance of your amplifier. It has real life effects. Okay, so where was I? Oh, yeah, impedance. So we said, I stated, right? equation here. That's the mathematical quantitative explanation. But let's look at what happens when you are actually just sending current through. Let's say you're applying DC to a inductor. DC frequency is 0. Inductor behaves like a short circuit, no impedance, 0 ohm impedance, right? When that incoming current changes as it does for AC, so input is now trying to change, the magnetic field is going to oppose that change, right? If it's just changing once, it'll oppose it a little bit and then stop, right? Reach a steady state. Let's say it changes again and again and again and again, over and over. It keeps changing. The more it changes, the more it opposes. So in terms of frequency, if it's lower frequency, lower changes, higher frequency, more frequent changes. So higher frequencies will have more opposition, lower frequencies will have lower opposition. So the impedance of an inductor is directly proportional to the frequency. As the frequency increases, the impedance increases. Lower frequencies, lower impedance. If frequency F is 0, impedance is 0, inductor behaves like a short circuit. Ties back to chapter 3. Capacitor is the exact opposite. It's the 1 over frequency. Okay, 1 over frequency. But let me explain a few other things. So we had ZR, impedance of a resistor R would be J times 0. Because a resistance does not have any reactance. A resistor does not have any reactance. So impedance for a resistor is simply the resistance R. A resistor behaves the same way for AC as it does for DC. No change. So there is no such thing as impedance of a resistor. It is simply resistor. That's it. ZR is just R. However, ZL, inductor impedance, ideal inductors do not have any resistance. So it's 0 plus JXL, meaning it's simply JXL. Okay, JXL. ZC is 0 minus JXC is minus JXC. I will explain why it's minus. So ZC is minus JXC, 0 minus JXC, because it does not have any resistance. So it's minus JXC. Okay. All right. So now we were talking about change in opposing the change in voltage, opposing the change in the input current. So in an inductor, what happens is you have an input current, creates a voltage, it opposes any change in that current. So the current is delayed. So any inductor you take, the current will always be delayed from the voltage by 90 degrees. So in graphical terms, it looks like this. If this was an inductor and you have a waveform, this waveform is, let's say, for the voltage of the inductor VL, then current for the inductor is here, and it is lagging, or it's behind the voltage for that inductor. Remember the time chart where we talked about phase. Y is equal to 0. Positive numbers means it's the future, meaning it is behind, it is yet to come. Negative numbers, meaning towards your left, is the past. It's already gone by. It's already ahead. So if it's ahead, meaning if it's to the left, then it's leading. If it's to the right, then it's lagging. Ahead or behind. Okay. For an inductor, for each specific inductor, the voltage for that inductor will always lead the current for that inductor by 90 degrees. So if you do theta VL, minus theta V, not V, IL. Phase angle for the inductor voltage minus phase angle for the inductor current will always be plus 90. Always, always, always. The size of the inductor doesn't matter. The inductor voltage or current does not matter. The value of the inductor, the value of the voltage or the current doesn't matter what it is, but the voltage and current will always be offset or out of phase by 90 degrees. There was one more thing. I don't know if I drew it out. I should have drawn it out there. Right here. This is a poor pun of a pizza. One pizza pie, but one full cycle is not one pi, it's 2 pi, right? 2 pi or 360 degrees. We are transforming a time varying function into a vector in the rotating plane. So you have a circle associated with that one cycle. One cycle, of course, is one circle, and one circle is not 1 pi, but it's 2 pi. 2 pi or 360 degrees. 1/2 cycle is pi or 180 degrees, and a quarter cycle is pi by 2 or 90 degrees. So in radians or in degrees, right? In radians, there's your circle. In a vector, we talk in terms of radians, 2 pi radians, right? 360 degrees. Half cycle is 1 pi, 180 degrees, and a quarter cycle is pi by 2, 90 degrees. All right, let's go back. Let's go back here. So again, that's where that comes from, 90 degrees. It's behind 90 degrees. Or phase shifted by pi by 2. A capacitor is the opposite. If you have a capacitor, now the current IC is ahead and the voltage VC lags. So VC lags and IC leads. And this is true for any capacitor. So the phase difference between capacitor voltage and the capacitor current is always minus 90. And that's why the impedance is negative. And it's not yet the full explanation of why it's negative. We will see that in the next slide. But that's where it comes from. Now, if you need help, we'll call on Eli Manning. Everyone knows who Eli Manning is? Not everyone, but at least some of you might know who Eli Manning is. He's the quarterback, or was the quarterback for New York Giants. And did you know he was known as the Iceman? Because he's got ice in his veins? Not really. The mnemonic precedes him. It's not named after Eli Manning. That's just, again, another one of my poor puns. Everybody knows by now what L stands for. And C stands for inductors and capacitors. I stands for current. Take a wild guess what E stands for. Voltage. Electromotive force, EMF. So in an inductor, the voltage is always ahead of the current, or voltage always leads the current. And in a capacitor, the current always leads the voltage, or the current lags the voltage. So plus 90 for inductor, minus 90 for a capacitor. Okay. Eli the Iceman. Now, let's go to mathematical operation and I'll explain. At this point, I would like to remind all students that if you have not yet looked at the worksheet, the complex numbers worksheet, again, I think I reminded, I pointed this out in the first week of class, if I remember correctly. You have to be able to program or perform complex number math on your own calculator devices. You need to be an expert in using your own calculators. I would not be able to help you with those, okay? And again, as a reminder, this math is not specific to EE. Math is generic. It applies to all engineering and all scientific fields. It's complex number math. My calculator is from the 90s, more than 30 years old. That's when I began as a student. And so while it can do a lot of things, I cannot program equations in there, unlike modern calculators, okay? You can take a very long equation, program it in a software or program it in a calculator, and it'll spit out a single answer. I can't do that. This is the way we used to do it back in the day. And again, this is good knowledge for students to have, right? We can perform all four arithmetic operations, addition, subtraction, multiplication, division, on any complex number. But some coordinate systems are easier to perform some kind of operations. So if you have a addition or subtraction, it is easier to do it if you have rectangular coordinates. And if you have multiplication and division, it is easier if you have your complex number in polar coordinates. I will explain how and why. Rectangular coordinates are the easiest for addition and subtraction. Let's say you have two complex numbers, a plus or minus jb, and you're trying to add or subtract another number, c plus or minus jd. It's straightforward in the sense that you combine all the real parts together and you combine all the imaginary parts together, and that's it. As straightforward as that, okay? Now, of course, you can do addition subtraction using polar coordinates, but it's just harder. It's a different kind of equations, right? This is all trigonometric identities, right angle triangle. If you're multiplying two numbers, let's say magnitude A, phase B, multiplied by C, phase D, the magnitudes are multiplied and the phase angles are summed up. Phase angles are summed up. If you're performing division, and this is going to be very important, if you perform division, magnitudes are divided. What happens to phase angles? Subtracted. That's the mathematical operation. So because I cannot program equations, I have to go back and forth. If I'm performing an addition in the same equation, I have to change from polar to rectangular. Then if I'm performing a division, then I'd go again, change from rectangular to polar. So I have to keep going back and forth all the time. But in a programmable calculator, depending on its functionality, of course, you can program an equation which has like polar coordinates and rectangular coordinates and all at once, and it'll just perform that operation. But again, you need to be an expert in doing so. Okay, so reach out to your peers. If you recall back to the first week of class, one of the questions I had in the discussion was, what brand, make, and model of calculator do you use? So if it's something that you're not familiar with, go through that list, find somebody, whether you know them or not, that uses the same model as you do, and reach out to them. Okay, there are resources online on websites everywhere. But that was the purpose of asking students to supply that information. So division, phase angles get subtracted. This is important because all our fundamental laws are applied as they are. If you have an inductor or a capacitor in a circuit and you wish to find the voltage or current, you don't have to integrate anymore. You don't have to perform a derivation anymore. You can simply apply Ohm's law and do simple math, except that math is now using complex numbers. That's the only difference. Okay, but you're not need to solve any differential equations. And that's the beauty of using this technique. Ohm's law, V equals IR, simply becomes V equals IZ. Remember, I said they're all synonymous to each other. So everywhere in our analysis techniques where we had resistors, right, chapters 1 and 2, you just substitute impedances Z in place of R. And it works exactly the same way. Ohm's law, KVL, KCL, everything is valid. We have to take phase angles into account. Imagine what fun would I have if I assigned a quiz with node voltage analysis and complex numbers. That would not be fun to grade, but it will work. You won't have to solve any differential equations. You won't have to solve integration, derivation, nothing like that. Okay. Non-E major classes, you can relax. We don't do any of those techniques. The most we'll do is Ohm's law, KVL, and KCL. Okay. So we won't do mesh current analysis and node voltage analysis using complex numbers. All right, so let's take a look at Ohm's law. V equals IZ, right? What does that mean? It means impedance is voltage divided by I. All three quantities are complex numbers. Voltage divided by current for that component, okay? Voltage divided by current for that component. It's a division of complex numbers, it's a division of phase angles. That means that the impedance angle is the phase angle of the voltage minus the phase angle of the current. Always, 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 because Ohm's law is fixed. Ohm's law is V equals IZ. So impedance is voltage divided by current. That doesn't change. It's voltage divided by current for a complex number is the phase angle of the voltage minus the phase angle of the current, which if you apply here, comes out to be plus 90 for an inductor and minus 90 for a capacitor. And so impedance for an inductor is always positive. Impedance for a capacitor is always negative. Plus 90, minus 90, always. If you recall back to chapter 3, I introduced these two components by saying they're very similar to each other, but in many ways they're also exact opposites. And that's where this is going to be very useful. Let's take a pause, 10-second pause. Think on all of that. Let me know if you have questions. Any questions? We'll look at examples next week. For now, we just want to take it slow and go over the concepts. Anyone? Okay. All right. It's a lot to take in. So even if you don't have questions now, you will have questions later. So please reach out, email, Zoom, in person. I'll be happy to explain. All right, so those are fundamental laws. Okay, so let's talk about KVL. Actually, before that. So VL, inductor voltage, is simply the product of the inductor current and the impedance. We don't have to perform an integration of the voltage, right? Inductor current is integral of the inductor voltage, but we don't have to do that. AC analysis, simply apply complex numbers, apply Ohm's law. KVL and KCL. Let's explain KVL because that's the lab you're going to do next week for those of you who are taking the lab. Let's say you have a DC circuit and you apply 10 volts to a 3 resistor network in series, right? 5 ohms, 3 ohms, and keep things simple, 2 ohms. Straight up voltage division, 5 volts, 3 volts, and 2 volts across each 3, right? If you plot the vectors for these DC voltages, how would they look? They would not have any phase angle, so they would be lying flat on the x-axis. So let's plot them. If you plot these, coordinate 0, 0, how would you plot them? We start with the 5 ohm resistor, 5 volts. Then it's a graphical illustration. We want KVL, right? So they should sum up to 10. So we plot the second voltage. The second voltage will be plotted where the first one ends. So it will be 3 volts at the beginning of 5. And lastly, the third one is plotted where the second one ends. So graphically, if you take this coordinate and you take this last coordinate, it should sum up to your total source voltage of 10 volts. Make sense, right? KVL works in DC. KVL also works in AC. But in the lab, let's say you're taking some measurements. You measure the voltages across all components, then you try to add them up. Will they sum up? No, they won't, because all you're measuring is the magnitude. There's no phase angle. There's no way you can measure the phase angle right there. It's just the magnitude. You'd have to take the phase angles into account. So the same example for AC would look something like this. You'd have your coordinates. You'd plot your first coordinate. Let's say it was 5 volts. So you vector with a length of 5 volts. And then you plot the voltage for either the inductor or the capacitor. You'd have to take the phase angle into account. The phase angle. And this is not for a single inductor. It's just for a system as a whole. Let's say this was like 4 volts. Who knows? What is it? Just random numbers. And then when you sum it up from the end point, from the start point to the end point, that vector would give you your total VS. If you add up just the magnitudes, it won't work. You'd have to add, or you have to take the phase angles into account. So lab 6, phasor diagrams, the actual procedure is not going to take long. You simply take measurements, and then you create a phasor diagram to calculate the phase angles. So KVL will still work, KCL will still work, except you're using complex numbers, so you have to take the phase angles into account. All right, questions? Does that make sense? Right? Verifying KVL. Yes. Arbitrary, yes, random. All the values are random. Just illustrating the point. Yes. Yes. So the question being asked is, where is the angle? And so this is the real axis. Is the angle would be. That's where the angle is. Good question. Okay. All right. So as I was saying, KVL, KCL, everything works. So how would it work? Well, we begin by doing resistive circuit analysis, and the analysis for AC circuits would work exactly the same. Okay. So let's say you had inductors and capacitors in a circuit. What you would do is you would represent these inductors and capacitors with their equivalent impedances. Their equivalent impedances. ZL and ZC. Inductors and capacitors are separate components, but if you represent them as their impedances for AC analysis, you can combine them. You can combine them because their impedance. Impedance is the exact same quantity. So if you have an inductor and a capacitor in a DC circuit, there's not much you can do about that. But if it's a AC analysis that you're doing, you can represent it with its impedance, ZL and ZC, and you can write in ZEQ as ZL plus ZC. Impedances add up the exact same way as resistors. So if they are in series, you add them up. If you're in parallel, the reciprocals. No difference. Everything works exactly the same. If they're in parallel, ZM, ZC. ZQ is ZL in parallel with ZC. Okay. So again, impedances, resistances, and reactances are exactly the same. They're synonyms of each other. The circuit analysis that you do is exactly the same. The symbols are the same. The units are the same. They combine the same way as resistors in series and resistors in parallel. Okay. And then one final slide is this one. This is for informational purposes only. We're not solving any problems with this, but this is something that students should be aware of. Okay. These quantities are basically reciprocals of each other. Reciprocal of resist is conduct, of react is being susceptible, so susceptance, and impede is admit. So reciprocal of resistance is conductance, reciprocal of reactance is susceptance, and impedance is admittance. Uppercase Y, uppercase G, and uppercase B. And the reason we do that is because when we have multiple components in parallel, it makes it easier to perform circuit analysis if you already work with the reciprocals before you begin your analysis. So if you have multiple components in parallel, you have admittance, you have reactance, you have susceptance, and you have conductance, it makes it easier to work with it. Otherwise, the equation just becomes complicated. That's the reason why we use it. Yes. Similar, yeah, exactly, yes. It's purely mathematical in that sense, it's mathematical. Conductance, of course, is like, it's real. It's the ability of a material to be able to conduct electricity or conduct electrons. So there is, of course, real physical basis for each one of those terms. But mostly, personally, I think of it just in terms of pure mathematical. You can solve circuits using the impedances, resistances, and reactances. It just would take a little bit longer and make the equations more complex. The unit is named after the German physicist Siemens. Oftentimes, you can also come across a word called mho, simply the reverse of ohm. Siemens or mhos. Okay. All right. We'll end class here today. If you have any questions, let me know. Send me an email. I won't have office hours at my regular time, but I'll be there in my office between 4 and 5. I'll post an announcement as soon as I'm able to. I'll bid you a good weekend. I'll see you on Monday for the quiz. The quiz will be based on chapter 5, only on the material that we have covered so far. So concept based. Not too heavy. I don't think I'm going to be too heavy. Okay. So not chapter 4, chapter 5. All right.